Hello, and welcome to Engineers Speak. Tonight's event is brought to you by the American Society of Mechanical Engineers. I am Francis Fish, President of the University of Delaware chapter of ASME. Tonight our guest speaker is Dr. John Tierney. Some background about Dr. Tierney. Dr. John Tierney is a senior scientist at the Center for Composite Materials at the University of Delaware. Dr. Tierney holds a Ph.D. in Material Science and Engineering from the university and has an honors bachelor's degree in mechanical engineering from the National University of Ireland. Dr. Tierney has extensive experience in design and processing of composites and has been conducting research in innovative processing methods for manufacturing composite parts. Dr. Tierney has led design engineering to optimal design of lightweight 105mm and 120mm composite overwrapped gun tubes as part of ARL's Future Combat Systems program with ARL and Picatinny Arsenal. He co-invented the rapid induction lamination process, RAIL, for the facilitating of the high-speed production of the M829E3 Sabo at ATK Rocket Center. He was design lead on a composite trailing edge flap for the Orion P3 with ONR Naviair and was co-PI on a recent STTR to develop a better understanding of material behavior for thermoplastic tape placement for NASA. He has also led on the development and implementation of high-energy test methods for thick section armor with ARL, which included modeling of bolted attachments under mine blast and ballistic impact. Currently, Dr. Tierney is working on two DARPA projects, one with open manufacturing related to rapid prototyping of composite ankle-foot orthotic structures, and the other for the Warrior Web program. Dr. Tierney is proficient in CATIA V5 as well as a number of FEA commercial packages. He often presents workshops to industry on how to apply these tools for composite design and analysis. Dr. Tierney is here tonight to talk about engineering design with an emphasis on computer-aided design, or CAD for short. I would now like to hand the podium over to Dr. John Tierney.
Okay, so thanks for attending. As you can tell, I'm Irish, and I've been here now half my life. Came to Delaware 20 years ago, back in 1994. I imagine a lot of you are young or not with us yet, but so I've been at this game a long time. As I said, I graduated from Galway on the west of Ireland as a mechanical engineer, and that was my first exposure to composites. There was a professor there, Croker O'Brady. He actually came to Delaware many, many years ago. At the founding actually of the composite center across the street. He was around at the infancy of that center. And so his exposure to composites, he kind of brought that back to Ireland, and I got exposed to composites, you know, from his experience. So that's kind of the reason that I'm here. You know, I learned from him and came over here, and I've been working in composites, you know, ever since at the center across the street there. I've been lucky enough to have a mentor in Jack Gillespie. You can almost think of him like one of the godfathers in composites. He's got many, many hundreds of publications. You know, his office is next to mine, so I can always go in there and bug him and kind of pick his brain on many. You know, I'm working in composites. All the projects or most of the projects I've had with him. So I've been really very lucky to have an insightful leader and a mentor, if you will, as Director Gillespie at CCM. And for those of you that have had the opportunity to work over there with him, you're really very lucky in that, you know, he brings a breadth of knowledge to the industry. The industry has been shaped, if you will, by his work over the past, you know, 35 plus years. So I've been really lucky to be really working with him. So when I came over here, you know, I originally was going to do a master's program, but Jack coaxed me into sticking around a little longer to do a PhD program, and I guess he's been successfully keeping me here ever since. And through all those years, I've learned a lot about you know, composites obviously, but also the way we model them, the way we design with them. I imagine some of you here in CAD are doing a lot of work in metals design with CAD. And a lot has happened over even my 20 years working, or 24 years really working in CAD and FE in terms of what capabilities out there now in designing, in using simulation. And that's much the same in composites. There's a lot of breadth and knowledge and tools for designing composites. That's how they design aircraft, vehicles, wind turbine blades. They do it all through CAD and FE simulation. And I've been involved, luckily, in all of those areas, which is really nice. Working at that center, there's a very wide breadth of projects in composites. And so, what I'm going to talk about today is a little bit about those tools that are out there. You'll be maybe familiar with some of them. I'll talk a little bit about how we have applied those tools to design, the methodology, kind of the way we design and the steps we go through if we want to have a metallic part, make a composite part out of it. What's the thought process? What are the steps involved to really design and optimize a composite? For those of you not familiar with composites, there's a lot of complexity with designing composites, but there's a lot of opportunity in that you can really tune the material, tune a laminate to really get the lightest weight solution. And that's been done for many years and applied for aerospace. Now there's a large push to get that into automotive, mass production. So that's a real big push. So you will see that if you're getting into the composites game yourself. And there's going to be a lot of industry really pushing mass production of composites for the automotive industry. So that's an area that if you are interested in, that's a really good opportunity. You may be familiar with the work that maybe BMW has done. We're actually working with BMW right now. They were really the first mass production composite vehicle with the I-Series. You might be familiar with the i3 and the i8. They went through great capital expense, great risk to develop the entire production chain for a mass-produced composite vehicle. And there was a lot of growing pains with that, not unlike the growing pains that one would have had when metals first were stamped for vehicles. And they've learned a lot, and now they're working with us, leveraging our knowledge in composites to try and really understand and optimize composites for dynamic events such as crash. The number one driver really with automotive is to make sure you design this vehicle safe. And so we're working with BMW and NHTSA, the US National Highway Safety Authority here, to really come up with a methodology by which we design a composite for the road and apply whatever we learn to the industry, publish what we learn and build like a framework for designing composites for automotive. But it's a very exciting growth area. It's also very exciting in that it's a very large market in terms of the use of composites. It's going to be very, very high volume. Weight optimization is going to be key with that. And so all these major industries, you got Ford, you've got Toyota, Hyundai, they all are working on developing composite vehicles. So not only will you have these driverless vehicles, but you'll have very, very lightweight vehicles, they're electric vehicles. So every way you can take off weight, that's good. The key then is to try and mass produce composites. And metals you can mass produce fine, they're stamp form, but with composites it's a lot more involved. We're trying to really make composites at high volume. So that's an interesting area that we're working on right now. So going back to what I'll talk about this evening a little bit is strategy in composite design. How a lot of times we're going from a metal structure to a composite structure. We've had the opportunity to work with a lot of industries that kind of come to us and say, I've got this part, I have no idea about composites. How would I go through the process of making this into a composite, and what would the hurdles be for me to really try and do that? So I'll talk a bit about that. The state of the art, I'm sure you're familiar with AutoCAD, SolidWorks. You may be using that as part of your projects. Those are standard tools now that have some composites capabilities. There are others, such as CATIA, which we use extensively. It's a very nice tool for designing not only just parts, but composite parts, and the full supply chain of how one would make these parts. And I'll talk also about the analysis capabilities. Now, what's happening now over the past 20 plus years is there's been a lot of mergers. Like there's been, in the past you'd have, say, Abacus, by itself as a standard FE solver, and you might have some sort of CAD program, and there was a lot of disconnect between the two. So what's happening now is these companies are buying these solvers, buying Abacus and the CAD and merging them into one environment. And what that does is it allows the engineer to really work seamlessly. You can design a part, you can analyze the part, you can send it off to be machined, all in one environment. And it really enables the designer. So instead of you going from trying to manage many different levels of the part in terms of here's a CAD file, I have to try and make it into an FE file, I now have to try and take it into a CNC part. You can now do that all in one environment, and it really allows the engineers to truly design. You now have a nice artist brush in order to design where you've got a good tool for you to come up with the final part. So you guys are lucky. There's a lot of nice tools out there that weren't there 20 years ago, and it really enables you to design. So I'll talk about some of those capabilities. And then I'll also talk a bit about what I've been doing in terms of the work I've done at CCM. One of my hobbies, if you will, if you call it a hobby, is software design. So it's also been very beneficial at CCM, where I've designed some composite codes that we use over there, and the industry has used, the government labs have used as well. And I'll also talk a bit about the future in terms of some of the software that I've been working on as well. So those are the three areas I'm going to talk about tonight. So, as I mentioned before, there's a lot of integration going on. You have the major players like, SolidWorks, CATIA, Pro-E, you've got Autodesk, and there are others. And what they've done now is, as I said, there's been a lot of joining of these technologies, or integration of these technologies. It's becoming more seamless now how one talks to the other. And not only that in terms of design, but also manufacturing. There's a lot of codes out there now that helps you understand how you would manufacture a composite. When you lay down fabrics, you can now predict how that laying process will happen, like how the materials will drape. So instead of you saying, you virtually designed the part, but now you really have to make it. You got to go out there and make sure that whatever way you're going to lay this material on this complex surface, that the layup is going to be the way you want it, the plies are going to be oriented the way you want, and you may have to cut the material in order for that to happen. You can now virtually cut materials and see what you're going to do with the part as you're making it. So in the manufacturing sense, there's all these tools right here available for you to do virtual manufacturing of composites. Then in parallel with that, then you have these structural codes, like you may have heard of Abacus, ANSYS, MSC software such as Patran, Nastran, Mark. There's a whole host of codes out there for doing structural design. But overall in the industry, really the players are less, but the capability is more. There's a few large players in the product lifecycle management that's out there, and what they've done is integrated all these capabilities into one environment. And it's become very, very useful for the engineer. This is just some snapshots of some of these codes kind of in action. Simulate is a piece of software that is essentially embedded inside of the CATIA environment. It allows you to do draping analysis. FiberSim is another big program. It was recently bought by Siemens. It allows you to lay down material, composite fabrics, and see how it conforms. And these red areas and yellow areas are potentially problematic areas. Like if you can just imagine laying down a cloth and you start to see it wrinkle. So there's tools out there to tell you you're going to have problems. So what you can do then is you can go in here and virtually snip it and see, is that snipping going to actually make it drapeable and drape over the surface? And you can also see what's that snipping doing to my structural performance. You've inherently weakened it by cutting the fibers. So you can then go ahead and predict, now that I've cut the material, is it still going to be okay? Can it take the loads that you're going to apply to it? You can also add multiple layers, and you can snip in different points, so there's no snipping going on in the same area. You're not locally weakening the part. So you can truly optimize that. And that's how they design, aircraft structures. That's how they design, wind blades, aircraft and vehicles. And another tool that's available from the ESI group is Panform. Panform is a little different. This tool is doing for dry fabrics. You've got glass and carbon fabrics that are dry and conform. This is more of a forming tool. Another process that's used extensively is thermoforming. It's kind of like stamp forming for metals, but in this case you're heating the composite up, softening it, and then you're forming it in a tool. The material behaves a lot differently. There's a lot of shear going on between the layers because it's really like a liquid, a heated liquid. So there's tools now available to predict how is that going to behave during that process. And then there's other tools as well. Laminate Modeler does essentially the same thing. You've got anaglyph laminate tools, and you also have now recently Altair's HyperWorks. This software as well allows you to do draping simulations inside HyperMesh. So these are some of the tools in terms of simulating the manufacturing process for composites. Now, one of the tools that we use a lot is CATIA. And the reason we do, it's really, there's many reasons. One of which is an integrated CAD. It's got integrated composite design capability. It has a lot of embedded capability to ensure you've got compliance with design principles that you have. And as I said before, because you've got this really nice unified environment, it really helps you concentrate on the design and not the tool. In the past, as I said before, you were sending parts from one environment to another environment. It's very cumbersome, but now CATIA is a tool set that keeps you in that one environment and working very well. The software that can also handle assemblies, so you can have composite parts and metal parts in the same design. You can connect them up, you can load them, see how they behave, it's all in there. The other thing is you can create plies that you can manufacture. You can actually send these plies to machines, right, to ply cutters, and really and make those parts, which is very, very nice. Producibility, which is also known as draping, as I mentioned before, it allows you to check, you can really drape this material, and it'll check and make sure that that can happen. You can visualize the way the fibers go. You can see if there's any manufacturing problems, as I said, such as wrinkles and bridges, which is basically the folding of the fabric, in a virtual environment. So this is one of the main, this is the reasons we use this software, and it's a very, very powerful tool for doing design. And just to give you an idea of the integration, most of the CAD software you have out there now is based on a tree. It's a nice hierarchical way for you to manage the information. And so they're all pretty much standard in terms of trees. But this is what a CATIA tree looks like. So on the right here you'd have your part, and this is the tree. And in here you would have your composite definition. So you might have some plies in here laid out on the surface. And inside the same tree, just a little further down, you have your analysis. So what you can do is you can add plies here in your design, and then load it up. Maybe I might have some loading condition, and see, okay, I've added a ply, I've dropped a ply. Is that weakening? You know, is it adequate enough for the structure? So it's very nice because you're doing that instead of having to modify geometry or plies and then feed that into an external program like Abacus. You're staying inside this environment, and you're really able to go through a nice iterative loop in terms of optimization. So that's what we do on a daily basis at CCM when we design. So these are some of the tools that are out there, and a lot of these tools that I showed you before have this tree type of hierarchy, and a lot of them have a lot of integration, whether it's even composites or not. But you can now design, as I said, without leaving one environment, which is nice, something that's not always been there, but now it's part of the standard. So when it comes to the design strategy that we use, for composites, a lot of times we're working with a metal structure. So we typically do, as a grounded example, a baseline analysis of a metal structure. That gives us an idea of how the metal behaves in the application that you have. Now you might have that design based on design drawings, or you may have to reverse engineer. There's been instances where we didn't have design drawings. We actually have to scan parts and scan surfaces of aircraft surfaces and try and get the true surface. These aircraft, or some of these aircraft, are like 40 years old, 50 years old. So some reverse engineering design drawings, do a baseline metal analysis. We know the design requirements. We maybe have some property data. And what we use a lot of times, if we don't have it for composites, we would do internal testing. We do some virtual software that we have, or there's other codes available as well. Or maybe the material supplier might have some information. And so we have a baseline metals analysis, gives us an idea of performance. We have data coming in from the composite design. And then from that, we now can work on designing the laminate specification for each layer, the laminate orientation, and the laminate thickness, the stacking of your laminate. And then all those tools I mentioned in the previous page we can use for doing the design. The CATIA composites design we use extensively. It has a lot of, as I said, it's got the fully embedded SD meshing capability inside the software, full analysis capability inside the software. We also have other tools from other vendors inside there as well. This is actually a Patran-Nastran solver. You can actually build a model inside of CATIA and run a Nastran model inside of CATIA as well, which is nice. And there's the option as well as running Abacus. So you don't have to leave this environment to actually create an Abacus simulation. You can do it all inside of CATIA, run Abacus externally, and then look at your results inside of CATIA again. And we, as I said, we use other tools. We may have to go look at using Laminate Modeler and FiberSim for doing draping simulations. And there's other unique codes as well. We might be interested in looking at how the structure fails. So here's one. This is AFC, Abacus for CATIA, with a virtual crack closure technique. We use that for looking at failure of the composite. These tools all embedded inside these environments, which makes it really, really nice for doing this analysis. So this is typically how we go from metals. We have all these tools available. We have all this data that we might build or generate, and we do our design. And these are the typical things we'll do. Draping simulations, you do obviously a structural analysis inside this environment. So this is kind of the design strategy that we apply for any project that has a metal to composite design. And so here's an example of one project we had, as Francis mentioned. This is one where we were looking at replacing the aging Orion P3 aircraft. And what they wanted to do was they have the P8 Poseidon now, which is their composite wing structure. So they wanted to see, with this particular structure, it's typical in aircraft, these hat stiffeners, they're locally local stiffness for the aeroelastic loads on the aircraft itself. And so this is typically an aluminum multi-skin piece right here, and it's all riveted together. And the problem they're having, of course, is these rivets, they're degrading over time. There's a lot of corrosion going on there. It's a stamp-formed piece. It might not look like many parts, but there's actually about 20 pieces here, all these skins that are stamped or riveted together. So they wanted to look at, okay, if we're going to try and make this out of composite, it'd be nice to make it as one composite piece. But the problem is, you know, you have all these bumps. And when you're laying down the material, how do you know you can lay it down without having wrinkles and problems like that? So now with these tools available to us, we're able to virtually see what happens. So what we did was we'd say, okay, let's just start off with one hat, right? Just don't worry about the overall global problem. Make it simple and say, if we can't lay down one hat, we certainly won't be able to lay down 20. So what we do is we use the software to figure out, okay, here's the original surface of that stiffener, right? That's reverse engineered. And we say we want to drape it. So we lay down this fabric, and we start from the center, and basically virtually lay it down. It conforms to the surface. And what happens is it seems to be doing okay here, but then it gets to the ends and it starts to wrinkle, right? So these yellow and red areas are telling us virtually you're going to have trouble. And we know that. We actually get a single hat stiffener. We saw that. But we have the capability to simulate it as well. This is for a 090 laminate, you know, a simple plain weave. And if you rotate it 45 degrees, you're laying down now a plus minus 45, and you see it behaves a lot differently. You still have the same problems at the end here. You know, you see these blue and red areas, or sorry, the red and yellow areas. And what they correspond to is a deviation of the ply angle. So what you're having here is you've got no shearing. It's laying down nicely, but what happens here is the material starts to shear. And if it can't shear enough, it starts to wrinkle, right? Just like whatever nearly all fabrics do. So what these colors here are, the yellow is 5 degrees and the red is 10, telling you that it's wrinkling 10 degrees beyond the original angle, 45 degrees that it was laid down. So here it might be trying to lay down 55. Now the simulation is going to try and lay it down no matter what. In real life, wrinkles happen, okay? It doesn't actually show you wrinkles here, but it's showing you that it's going to want to shear and it's going to want to wrinkle. And so what you're doing here in a virtual environment is you're assessing the feasibility of making this. So what you can do is you can say, okay, let's change its shape, okay? So we'll make it nice and smooth, right? We'll kind of straighten out the ends here. Now in doing so, you're going to change its characteristics, right? It's got a certain bending stiffness requirement. So what you're doing here is, okay, you can, inside this environment, we can modify its shape, load it again in bending, and maybe tweak the height, maybe tweak its profile, and do that a number of times until you get the same stiffness, bending stiffness, but now you know you can make it out of this fabric. And what you see here is we modified this shape. It's slightly higher in the center, slightly broader in the center as well. And you can see here, this is the 090 fabric, no problems. The plus minus 45, we do start to see a little bit of problem area outside of here, but the overall hat itself is fine. So there's no problem within the hat, which is the area that we're interested in. So then we learn from one hat, you extend it to all the hats, okay? So here's a simulation of the structure again. And what we do is we start laying the fabric down at the center, and we start, flattening it out. That's what the software is doing. It's starting in the middle and virtually like laying it out. And you see, once again, you have all these problem areas along the edges of the hats. So what we do is, these are 3 simulations where I vary that shape kind of progressively. And you can see here, when I go to my end shape, all the yellow and red has gone away. So now we can actually get a single sheet of whether it's a 090 fabric or a plus minus 45, you can lay it right on there and have confidence that it won't wrinkle. And we did, and it was not a problem. And this is just a simple example of using virtual tools to guide the design process. So that's an overview of the tools that we have available in terms of FE and CAD. And what I wanted to talk about as well is, in the earlier slide I did mention in the strategy, before we even get into the CAD environment, a lot of times we want to know what are the baseline properties. What is the properties of a ply or a layer? And so the nice thing is we have a lot of tools in-house at CCM that we've developed, and one of them, one of the ones that I developed, was called CDS. And what that allows you to, what it basically is it's an advanced scientific calculator for composites. So it allows us to say combine a fiber and a matrix and predict how those two will work together in terms of stiffness and strength. And so these tools were derived from very basic kind of DOS programs in the 80s, and we've now streamlined it, and now it's at version 3, and it's a nice, simple graphical user interface where you can do create virtual plies and look at the stiffness and strength of those plies. You can also create virtual laminates. So think of it as before you even go off and do a full-blown FE analysis, you can basically get an idea of, well, what sort of materials should I be using for this FE analysis? This gives you kind of a ground zero assessment. You shouldn't always just fly right into a very complex analysis with a very complex design. Start simple. Like the old engineer would start with a simple calculator. Hand calculations can get you 70% of the way without all these iterations in an FE analysis. So this is a very nice tool kind of from the ground up. And it's not the only one. There's a lot of tools out there for doing this. But you know, we built this tool internally. And it's not just for simple ply or laminate design. There's other tools in here as well. We actually do, you can actually design cylinders inside this software. You can design, you can do other types of analysis as well. Beyond just mechanical, you can do thermal analysis too. And this is kind of a breakout of some of these codes. So not only can we do, you know, simple plate mechanics, like I mentioned before, and this is a very good way to assess a simple layup, if you will, to see how it behaves in plane or even through bending. But we can do thick section analysis. We can do even virtual cylinder design. We can look at how it fails virtually, you know, using whatever laminate design we do. And we actually have codes that actually feed into that. One of which, as I mentioned, we can do micromechanics, which means we can get a fiber in a matrix and build a ply and put that inside of a plate mechanics analysis. And we can then go back in here and tweak maybe the fiber. We could tweak the fiber volume fraction and see what it does to a laminate. Okay, so that's a very nice way to assess, you know, what performance, how performance of a laminate is affected by the constituents of the laminate. And so these tools are available, and anybody here wants to download it and try it out, I can certainly give you the links to do that. And there's other codes in here as well in terms of processing. Cure kinetics is another code, so we can actually predict how materials cure through heating, and we can also predict how they shrink. And we also have other codes in here as well that feed into, you know, whatever design we're looking at. So this is an example before you even go into CAD. You can do a lot in determining how a composite will behave using these tools. This is the interface if you do decide to download it. What it is it's fairly simple. It's a single window. It's a PC based, sorry Mac. And basically you have on the left a lot of materials. A lot of the material properties are already populated and available for you. There's about 90 materials in here. There's about 10 different laminates kind of examples. And there's a bunch of different analyses already built as well. So what you can do in the tree here is you can literally just click any material or micromechanics input or laminate, and it will show the input of that analysis here, and it'll show you the results down here. And as I mentioned before, the input here could be a layup. You know, you might say, well, I'm going to make this part or this composite, and I have, based on my method analysis, I know it's got a certain stress, it's got a certain stiffness requirement. In here, you can virtually design that laminate. You know, add and drop plies on the fly. It's a real-time solver, so that you can figure out fairly quickly. Like, I need 16 plies of material at a minimum of, say, carbon, or I might need like 25, 30 plies of glass. But then it starts to get a bit heavy. So you're starting to kind of do simple assessments of what are the candidate materials, the candidate layups that you can actually use to replace this metal structure. So that's kind of an example of what you can do in there. And there's a lot more you can do as well. But that's what we use it for across the street. So this software, it's been out now for over, I'd say, 7-8 years in this form. And it's a nice tool for going from mechanical property inputs to a virtual result of stiffness and strength. And so that's all good and well as a scientific calculator in that regime. But what we want to do is think of beyond that. There's a lot more data associated with the composite beyond just its stiffness and its strength. There's information about the source of the material, the lot information, who made it, who tested it, all this information beyond just property inputs. And so what I've been working on is coming up with a new intelligent framework for data management. And what this allows you to do is create an open format for managing all this data. There's a huge amount of data when it comes to a composite. When you combine a fiber and a matrix, there's a whole wealth of information about the fiber and the matrix, beyond just properties. So what we wanted to do is have this framework where we capture all that information, whether it be the people that manage these materials, whether it be the test labs that test these materials, the models used to predict properties, okay? Storing all this information on the cloud, the process by which this part is made, the materials, as I said, used, the test equipment and how it's reported. So what we wanted to do was create an open method by which all this information is managed. And what we've done is I've created this software called Smart Tree, and it's an open XML format, just like HTML, but it's in XML. It's a very basic language for storing information. And what I've done is created a nice simple client for you to build information. So before I show you the interface, I wanted to explain, so what are these smart trees? And an XML tree is essentially, as I said, it's a very simple way to represent data. So what I wanted to do was build these trees that have some intelligence embedded in them, and also some tagging ability embedded in them. And I'll talk a little bit about both of those. So, as I said, a smart tree is a simple tree structure comprised of elements. And what the client allows you to do is build this information very quickly with very little input or manual input required to really build libraries of trees. And these trees could be trees of material properties, they can be trees of a process, they can even be trees of people. And you can build these trees and build a process or a part out of these trees and build those. And you can also use it to track production and workflow. For instance, if I'm making a composite, I can have a resin tree and a fiber tree, combine them together. I've now made a ply tree or a laminate tree, and then feed that into a part tree. And then that feeds into an ASTM test tree. So you can just imagine you can quickly build these trees, and by the end of it you have this master tree that has all this information stored. And the idea here is you can disseminate who manages and stores these trees. For instance, the guy in the Instron lab, he'd have trees for all his Instrons, and he'd have trees for all his strain gauges. So if a student walks in the lab, I'm using this strain gauge, I'm using this Instron, I'm using this load cell, he will just drag those trees into his ASTM standard, and without typing anything, he's now has a nice snapshot of all that information that he did while he was in the lab. We can even have trees for sensors. So for instance, the temperature in the lab, the moisture in the lab, there can be a smart tree just sitting there capturing that, and you drag that into your master tree. So it kind of grabs an active piece of information and makes it passive inside the master tree. The other nice thing about this software is I've added the capability for the client to capture what are called smart tags. So I'm sure most of you know Twitter, these hashtags. So what you can actually do in here as well, say I've got hundreds of these trees. Well, what you can do is you can tag the information within the tree. For instance, if I'm using a carbon fiber, like an AS4 fiber, you can have an AS4 smart tag, which means the moment I go into the client, I type in AS4, it'll tell me everything about AS4 in the building, who has it, who manages it, all the AS4 data, material property data, all that information pops up in an active search. So these smart tags are just like hashtags. They index the information and it's available for you to do. The other thing about the client is we can actually bring in external content, which means that we can not only just build smart trees, but we can also bring files into these trees. Files might be Excel spreadsheets of your test data. Files can be photographs, pictures, photo micrographs. You can actually drag them into your tree as well and store all that information into a master tree. And the other nice thing is the software is linked to user documents. When you bring the files in, you're not actually bringing that big file. It could be 2-3 megabytes. What you're doing is bringing a reference to it in. So all the files are still kept the way they are, your Excel spreadsheet. But there's a link made inside your tree, so if you click on that smart tree element, it will take you to the data. So it keeps the database size to a minimum, which is really nice. The other nice thing is you can actually build templates. So in the software that stands right now, I've got about 30 ASTM standards. If you've ever worked with ASTM, it's usually a 10-page PDF file. You have to interrogate it, figure out what's required, what's optional. So in the smart tree, there's logic built into these trees, which means I can build an ASTM standard for a test and give it to you. And you now know the hierarchy by which that ASTM must be followed. And inside that, you can have logic to say this piece of information is required or optional. So the tree is always tested for the content of itself. And if I was to put information in there that was out of spec or out of range, it flags the tree. So you can actually build logic into these ASTM trees, smart trees, and when I give it to somebody else, it'll make sure that they follow it, without having to interrogate an Excel spreadsheet. I know that if I send everybody out here to do a test in the lab, they come back with 200 different Excel spreadsheets. They might all be fine, but I'd still have to interrogate each one of them, like, is he doing it right? Like, is all the math correct? The software is designed to build these templates that I can share with everybody, and they'll all come back to me with the same tree. The tree will be identical. I'll know by looking at it. I'll also know if there's something wrong with it. And so that's the way it works. And as I said, it's all simple XML. So anybody has access to the format. Most of you may know what XML is. That's what it looks like. This is an example of a smart tree single element. And this is the actual client. So here what we have is on the top left is we have our libraries, and this is where all the information is stored. Down here we have a preview, and on the right we have a smart tree. And in the smart tree we've got all these elements. And the elements can be text, it can be dates, it can be a selection, it can be files, images, whatever you want in there. But you can build a tree and have it be a format. As I mentioned before, there's many different types. In here I've got a bunch of different AST entries. And so you can actually build a tree, apply logic inside the tree, and then, as I said, save that to the user community. And now they have available a very simple tree hierarchy. And as I mentioned before, a tree hierarchy is where all the codes are going. You know, all the CAD codes. Tree is very easy for you to interrogate the tree. What's important? Who wants what? There are child and parent elements in there. So there's a really nice way to logically build a tree. So that's kind of the idea behind this software. And these are the elements, as I mentioned before. It's kind of hard to see here, but the elements within a tree that I've built so far are headers, text, dates, selections, material trees, laminate tree. You know, there's really a whole host of things I've put in there to get things started, but you can actually build a lot more. And there's a whole lot of logic. Each one of these elements here can have its own logic, whether it's greater than, less than, equal to a value, if there's information missing, if the selection is wrong, you know, things like that. These are conditions of logic. So that's the idea. One of the other things I mentioned before is what we're trying to do is have a tagging, just like hashtags. So what you actually have is you can actually create a property smart tree, and these would have just properties, which would have values and units. Okay, these are the child elements of that. And so what you can do then is, using this property hashtag or property tree, it will search all your materials in your smart tree libraries and pick out the properties that are in this property tree. So for instance here, if I have stiffness, you know, in the one direction, it would look in all my libraries that are all smart tags, and then make those properties available for me to have it inside a model smart tree. So this model smart tree could be a laminate analysis. So all the properties are immediately available to you as well. Or it could be available to an ASTM smart tree, or a mid-handbook smart tree, or even a process smart tree. Whatever information you have in, say, a property tree is fed forward into the end-user trees, which might be models. So this is kind of the direction that we're going with that. And there's a website that goes in much greater detail, tells you all about it. You can download the software. There's a whole pile of examples, ASTM materials. I've got 50, 60 materials in there, a bunch of standards and things like that. So that's kind of you know, where I'm going with that. But, so what I wanted to wrap up with is give you a summary of the CAD. Just, and the other thing is, don't just dive into CAD. Always try and use the simple tools to get you started, especially in composite, and feed it into CAD. And there's a whole host of tools out there available in composites for doing design that I wish I had 20 years ago, but we have them now. And you know, the area of composites growth is exciting. Is another thing, especially in automotive. You know, the word on the street. You know, I go to a lot of conferences and I see that's a very big, you know, a lot of chatter going on in automotive for composites. So hopefully, for some of you here, that'll be an area that you'll like to get into. So, with that, that's the kind of a summary of you know, what I do, if you will. You know, the tools I have at my disposal. Some of the tools I'm working on, maybe some of the tools that I worked on that maybe 20 years from now you'll look back at this talk and say you were at the talk. So we'll see. But yeah, so thanks for your time.
We're now going to start our directed question portion.
Yeah, it was a bit long. Sorry about that. This is the cheese at the moment. I don't even know the actor studio.
All right, so excuse me. What was the proudest moment of your career?
The proudest moment of my career is, well, it's hard to say. There's a few. I think, you know, seeing success in your work, you know, seeing, you know, the designs that you work on come to fruition and be made into real parts. You know, there's a couple of patents that we've had. There's some more in the pipeline. I think also garnering the respect of my boss. You know, where, you know, there comes a point where, you know, you're always listening to him, and then it kind of switches to him listening to you, and it's nice to know that, you know, you have his ear and he has yours. So I think, you know, that happening to you wherever you are, it becomes a proud moment in your life, because now you know you've kind of bridged that step where you get the respect. You know, you're always get a point you're learning, and then you kind of switch over to being the mentor. And so I think it was really nice for me to to go from like always just kind of figuring things out to being able to really kind of switch the valve, if you will, and get information out to people. So that, and that was kind of a gradual process. It wasn't like an instant milestone, but it was just, you look back over 20 years of doing this, and you find students knocking at your door more than you knocking at other doors. And so I think that was a gradual milestone, if you will. But a lot of projects that I've worked on, just seeing them come full circle, like, see them out there being successful, those are the incremental milestones as well I've seen, over the years.
All right, the flip side to that coin, what has been your greatest struggle?
Well, struggles. When you have, juggling a lot of projects and, they fall behind, it's inevitable. We have a lot of different projects across the street, and some, deadlines come and go, and you don't always make them, So I think there's been instances where, I wish I could have gotten further in some of those projects than they were. But that's, that's the nature of the business. It happens to everybody. It's going to happen to you. So that's probably my biggest downfall, is like when some of these projects, the company you're working with is like calling you and bugging you, like, why aren't you getting this done? And you're trying your best to juggle them and others, and so that's probably been the biggest drawback, if you will, or so.
All right, questions. So we're going to open it up now to audience questions. Give you all a chance to ask what you want.
Yep.
How many of those integrated software packages are like feasibly available to students like myself?
Yeah, good question. Something like CATIA is for academic programs. It is affordable. We have an academic license for it here. I think we have a number of seats here available. We use it across the street. I think we've got like 10 seats. We do have one commercial seat because we have programs, that are not basic research. So CATIA is one. The other one is Autodesk. We have it here at the university, and there are some capabilities in there for doing design, composite design analysis. But when it comes to the big, the full PLM, it is very difficult to get your hands on something like that. I think CATIA is probably the closest, if you can get the academic seat for that. I don't know of anywhere where they're using the Siemens PLM, at least in the US, or I don't know if many universities that even have access to that. But CATIA is available to colleges at an academic level. And the nice thing is you get all the tools. CATIA, there's different levels. There's like P1, P2, P3. We have what's called a P2, and that gives us access to about 60 modules. And some of these modules, in a commercial sense, go anywhere from $5,000 to $30,000, just one of them. Having that in an academic, having all of them available, it is possible, and it is there. So if you're doing a project that has the right amount of funding, it's certainly feasible, for your basic research to get your hands on that. Any other questions? Yes.
Did you have any concentration or interest in composites during your undergrad?
Yes, the professor I mentioned before, O'Brady, my senior project was with him on composites. I had two projects. One was on an offshore riser connection, for offshore drilling, the pipes for carrying the oil. It's typically, it's a composite tube with a titanium fastener at the end. So my undergraduate project was to look at modeling that in Abacus, very, very early version of Abacus, all text input. And so yeah, that was my first exposure to composites in Ireland. The other one was on a material handling system for thermoforming. So it was like a picture frame, and you'd have a blank, and you'd feed it from a heater to a stamper. And so I had to design that assembly. So that was my first exposure to composites undergrad. And Francis, even before he joined the college, he was very motivated. That's the one thing I really liked about Francis, was he kind of got involved before he got to college. He kind of was ahead of the game. He was already knee-deep in composites, even when he got started. So I think it's very important to get started, have that motivation. Don't be afraid before you even go to, it's probably too late, you're all here now. But if you have brothers, sisters, friends, get them on before. I have a very good friend of mine, he works at Gore in Germany, and he started here in high school as well, very successful in Europe. There are others, another friend of mine, he's bringing his cousin in, he's not in college yet, he hasn't picked where he's going. But just, get in the game early. There's no mistakes made, when you get in the game early. You're always going to learn. So I think, I was lucky in Ireland to get exposed to this unique material, composites. he was handing around some of his samples that he made when he was over here, and I was like, wow, so I kind of got awestruck with that. And that's what got me involved. So. Any other questions? Yeah.
So the auto industry, what about recycling? What about the end use?
Yeah, the recycling is a big thing. The issue with recycling is, right, that there's two major forms of plastic used in composites: thermoset, thermoplastic. Thermoset is not what you can do. You typically you cure it once; it's a done deal. And the only way what you can do is you can kind of grind it up and sort of have it as in another material, in another part. Thermoplastics, on the other hand, you can reuse. And if you can get thermoplastics with the same resin throughout the whole part, you can certainly, reform it, remelt it, reuse it. Maybe not for the same application, but it still has some capability to be a structurally enabling structure. You're not grinding it down to a weaker structure. So there's that. There's also recyclable materials coming out now where you can actually break the thermoplastic back down to its like monomer and then use that as well. So you're basically bringing the material back to its virgin, unpolymerized state. And so that's another option. So you can completely recover the resin out of the composite, and you can almost completely recover the fiber. But that's a big deal, because in automotive you're talking, tens of thousands, millions of tons of material. And in the steel, you get it all back for the most part. But in composites, now you're going to be dealing with that same amount of material, if it ever gets widely adopted. So recycling is a big problem. That's why we're working with thermoplastics with BMW to try and see if we can recover the material. And that's the same also in the wind industry. You've got these massive wind turbine blades. What are you going to do with them? These massive 60, and they're only getting bigger. And they have a shelf life. Eventually, after so many years, you got to do something with these large structures. So there's some potential for thermoplastics for that as well. Try and use that. But there's a lot to be learned in trying to adopt thermoplastics. And for high volume production. That's another big bottleneck right now. Is composites are good in batch, small, or if you're doing a large structure, you've got a lot of manpower involved with that. But with mass production, you're splitting out, tens of thousands of parts. And so you want to be able to do it like a forming, stamp, boom, done. You don't want to be trying to deal with like infusion when you're drawing in resin every time, because for those familiar with resin infusion processes, there's a lot of variability in the material. You lay down 2 layers of fabric that are identical, and you infuse it, and you do it again. You'll get a different time to infuse, just because the way the materials kind of sit on top of one another when you just lay fabrics down. They have a different flow of permeability. So there's those things like that have to be addressed. So it's a little bit long-winded question, but thermoplastics are promising. Monomer recovery is another area. Any other questions? Yes?
So what was the project that you personally thought was the most impressive thing you've done? Like one you thought was the coolest, something you made that you were like, wow, this is really impressive.
There's a couple. If you ever get a chance, there's a robot across the street that I've worked on. It's called the AMP, Automated Materials Placement, and it's probably the most complex engineering design that I've done. There's thousands of parts in there. It's a fully automated system for laying down and processing both thermoplastics and thermal sets. If you go on the CCM website, you'll see pictures of it. So that's probably one of my, because it was a very technically complex machine. It's a one of a kind. There's nothing else like it out there. The other nice thing I liked about it too was I had it wasn't me just building it. I had I'm on now student number 9 adding to it. Like a lot of German students have come over working on it. There's a couple of US students working on it. Maybe one still working on it. In this room, and so it's evolved, and so for every student that's come and gone and worked on that, I like to think that I've kind of moved them down the road and becoming really good at doing composites automation, which is a big area. And so between designing that piece of equipment and all the students that got involved, and the success at which one student would pick up what the other one did and then keep on going, has been I think that's one of the biggest milestones. The other projects I've had where there's been patents and whatnot, it's all good and well, but a lot of that machinery I don't see anymore. It's down in West Virginia, it's some hidden building, doing something that processing a lot of material. But I don't see that, but I do see the robot, and I do see the students working on it, and they go from somebody that might not know LabVIEW or know Robot Studio, and by the end of it, they know more than me, and I'm getting lost now, like how are they doing this, and I'm playing catch up with them. So that's been very rewarding to kind of see that progress. So. Any other questions? behind me clear.
For those of you who don't know, there's actually a picture of the robot he's talking about on the wall here in Spencer.
Used with permission. So,
We have time for a couple more questions. So,
anything, ask me about anything, first thing or otherwise. But I've been here now half my life, and I'm very happy. I mean, obviously if I didn't like it, I would have gone off to industry many years ago. And I think it's just the environment that I've had across the street. We're very much an open door kind of policy in terms of how we work together. A bunch of smart guys, and they know different parts of the composite design process and manufacturing and fibers. And so it's been great that we kind of pool our resources together. If you're lucky enough in industry to get out there where you're working with that type of team, where you've got everybody got the right strengths, there's not conflict or whatnot, you kind of all supplement one another and use each strength, and then you kind of fit in there and get good at one thing or a few things, and then help the team that way. That's really why I've been doing what I've been doing for so long, is that that's the environment I have. And there's a lot of success out of it, with Gillespie as leader, kind of keeping an eye on his flock, but knowing that we all know how to do what we do, so that's good.
all right, there are no more questions. Speak up now. All right, let's give Dr. Tierney one more. Don't go anywhere just yet.
In an hour.
Alright, this is a little something that we've grown used to doing for our students that come here. I'd like to present you with a groundbreaking pencil made in a 3D printed case right here on campus.
Very nice. Thank you very much. All right, thanks, Francis.
Thank you. One more round.
Excellent. Yeah, I have a program right now actually doing 3D printing, 3D systems, and what they're doing right now is they're trying to optimize the process. One of the things about 3D printing is it's very difficult to get the neat resin. When you have injection molded parts, you get a lot of stirring and mixing of the polymers, you get very good quality. But with 3D printing, what happens a lot of times is if you were to cut a 3D printed part, you'll see a lot of porosity. It's like you have these tubes in fused deposition modeling or processing. It's like you're laying down spaghetti, if you will. And if you look at that, it's not fully fused. You end up with these nice little diamond holes, between each spaghetti as it's coming together. So we're working with 3D systems right now and trying to make sure that we get the same quality in the build. So this is kind of fitting, I guess, if you will, to get an almost perfect 3D printed part. So yeah, thanks again, everyone. Thank you.